you're flying a kite on a breezy afternoon in Central Park. You want it to soar high, but without a string to guide it, it might just drift aimlessly or crash. That's kind of like reinforcement learning without the stabilizing force of supervised fine-tuning. Today, we're diving into a paper that puts RL and SFT head-to-head, comparing their generalization capabilities for foundation models. Can RL truly achieve liftoff on its own, or does it need SFT as its guiding string? Unlike previous studies that focused on just one modality, this paper analyzes both LLMs and VLMs. Let's dive in.
All right, let's dive into this fascinating study comparing SFT and RL in foundation models. The big question here is, how do these two approaches impact a model's ability to generalize? Meaning, can it apply what it's learned to new, unseen situations? Spoiler alert, they behave very differently. To test this, the researchers set up two environments. First, there's General Points, a text-based card game that challenges models to do arithmetic reasoning. Then, there's VIRL, a navigation task that requires spatial reasoning. The goal? To see if models trained with SFT or RL can handle new variants of these tasks. And here's where things get interesting. RL, especially when trained with outcome-based rewards, shows strong generalization in both textual and visual tasks. SFT, on the other hand, tends to memorize the training data and struggles when faced with something new. But don't write off SFT just yet. It plays a crucial role in stabilizing the model's output format, which actually helps RL do its job better. So, the big takeaway? If you want a model that truly generalizes, RL is your best bet. But if you want to make RL training smoother and more structured, SFT is still a key player. Now, let's dig deeper into how RL and SFT handle generalization, especially when tested in new action spaces. The results are pretty striking. Take a look at Figure 1. It shows performance on the VIRL navigation task, where models are tested on both familiar and unseen variations. RL adapts beautifully to out-of-distribution tasks, while SFT's performance drops significantly. This tells us that SFT relies heavily on memorization, whereas RL actually learns to generalize. And it's not just text-based tasks where RL shines. In visual tasks, RL also outperforms SFT by a wide margin. This suggests that RL is a more flexible learning approach overall. One key insight here is that RL's generalization improves when it's trained with outcome-based rewards. This makes sense. If the model is focused on achieving the right outcome rather than just mimicking training data, it's more likely to adapt to new situations. So if you're looking for a model that can handle the unexpected, RL is the way to go. Next up, let's talk about two important ideas: inference time verification and improving visual capabilities in vision language models, VLMs. First, inference time verification builds on the idea that scaling up computational resources during inference can boost performance. The study tests this by integrating verification into RL. Instead of making a single decision, the model gets multiple steps to refine its responses. And guess what? The more verification steps, the better the performance. This shows that scaling up inference time verification is a big factor in RL's ability to generalize. Now, shifting gears to VLMs, these models are great at solving complex problems, like reasoning through exam questions or understanding spatial relationships, but they still struggle with visual perception. Previous work tried to fix this by adding high-quality training data, or fine-tuning the visual backbone. This paper suggests a different approach, using RL to enhance visual perception. The idea is that RL's generalization capabilities could help VLMs better process visual information. Finally, the section introduces some key RL concepts, setting up the mathematical framework for how states, actions, and rewards interact. This lays the groundwork for understanding how RL can enhance both textual and visual understanding in foundation models. Let's talk about a cool technique called sequential revision with a verifier. Instead of making a single guess and moving on, the model gets multiple chances to refine its answer based on feedback. Check out Figure 2. It shows this in action with a simple arithmetic task: compute 24 using 4 given numbers. The model proposes calculations, and each attempt is checked by a verifier. If the calculation is wrong, the verifier gives negative feedback. If the model uses an illegal number, the penalty is even bigger. But when it gets the right answer, it gets a positive reward. This setup forces the model to learn from its mistakes, rather than just memorizing responses. Figure 3 takes this further by showing how past answers and feedback are incorporated into the next prompt. Each new step builds on what's already been generated, helping the model improve iteratively. This structure is great for improving reasoning skills, because the model isn't starting from scratch each time. It's learning and refining as it goes. The section also introduces visual and rule variations in tasks. For example, in the general points game, models must recognize numbers on playing cards, even if the colors change. In VIRL, the model has to identify landmarks and match them with navigation instructions. These variations test whether the model truly understands patterns or if it's just memorizing the training data. The key takeaway? Reinforcement learning with verifier feedback helps models improve step by step, making them more adaptable and better at generalization. Now let's focus on VIRL, where the model has to navigate real-world environments using both text-based and visual information. Take a look at Figure 4. It shows how this works. The agent starts at a given location and receives step-by-step navigation instructions. It has to recognize key landmarks, like restaurants and shops, to figure out where it is and how to move. Instructions like turn slightly right or make a sharp left turn guide the agent's movements. If it correctly follows these directions and identifies visual landmarks, it reaches the goal. The big question here is, how well do models generalize to different environments? The study runs several experiments to test this. One experiment looks at how models handle different rule variations, like interpreting playing card symbols as letters or numbers. Another tests visual generalization, where the model is trained with one color of cards and tested with another. The results are clear. RL generalizes, while SFT memorizes. RL consistently outperforms SFT when tested on unseen variations, meaning it actually learns adaptable strategies rather than just memorizing training data. This is especially true in multimodal tasks that require both textual and visual understanding. In short, RL's flexibility allows it to succeed in novel situations, while SFT struggles when the environment changes. Let's dive into how well RL and SFT generalize to new environments, especially when tested on variations they haven't seen before. The results are crystal clear. RL adapts while SFT fails. Check out Figure 5. It shows success rate versus computation plots. In familiar environments, both RL and SFT improve as computation increases. But when tested on out-of-distribution (UD) tasks, RL continues to improve, while SFT completely breaks down. RL's performance stays stable across pure language and vision language tasks, while SFT shows a steep decline in accuracy. Figure 6 makes this even more obvious. It shows out-of-distribution success rates for different tasks. RL consistently outperforms SFT in every setting, with massive improvements in vision language tasks. In one case, RL boosts accuracy from 35.7% to 45.0%, while SFT collapses from 35.7% to just 2.5%. The trend is clear. RL is far better at handling new variations, while SFT gets stuck memorizing the training data. The discussion then shifts to visual generalization. Since vision language models process both text and images, their ability to adapt to new visual environments is crucial. RL once again proves its strength, showing consistent gains in generalization, whereas SFT fails to cope with new visuals. The takeaway? If you want a model that truly generalizes, whether in text or vision, RL is the way to go. SFT just memorizes, and that's not enough when facing real-world variations. This section dives into how RL and SFT handle visual variations in out-of-distribution tasks. The results? RL thrives, SFT collapses. Take a look at Figure 7. It shows performance trends as models process more computation. RL steadily improves its out-of-distribution success rate, while SFT remains stuck at low accuracy. The bar charts reinforce this. RL reaches 41.2% success in GPVL and 77.8% in VIRL-VL, whereas SFT lags far behind. This proves that RL adapts to new visual conditions, while SFT memorizes its training data and fails when tested on something new. Figure 8 digs deeper into recognition accuracy versus success rate. The x-axis tracks overall performance, while the y-axis measures how well the model identifies key inputs. RL consistently improves both recognition and task completion as post-training computation increases. In contrast, SFT shows performance drops of nearly 10%, meaning it struggles to adapt when faced with unseen variations. The discussion then shifts to visual perception in vision language models, VLMs. Since these models process both images and text, strong generalization is essential. RL once again proves superior. Scaling up computation enhances both recognition accuracy and overall performance. Meanwhile, SFT's reliance on memorization causes it to deteriorate in OD tasks. The takeaway? If you're working with vision language models, RL is the key to real-world adaptability. SFT just isn't built to handle novel situations. All of this might leave you wondering, do we even need SFT if RL outperforms it so handily? Interestingly, the answer is yes, at least when your base model isn't great at following instructions from the get-go. Check out Figure 9. It shows multiple RL training runs, all of which fail completely when applied directly to a base model without prior SFT. The problem? The base model just doesn't follow instructions well enough. Without SFT to stabilize its outputs, RL has nothing meaningful to refine. Figure 10 shifts focus to another key factor: verification iterations. The graph compares how models improve with different numbers of verification steps. The trend is obvious. More verification steps lead to better out-of-distribution performance. Under the same computational budget, models trained with more verification steps show significant improvements in both in-distribution and OD settings. The conclusion ties everything together. RL is the clear winner for generalization, but SFT still has a role. It helps stabilize models so that RL can actually work. Without SFT, the base model struggles to learn from RL training. Meanwhile, scaling verification steps is another crucial factor, as it allows models to refine their understanding better over multiple iterations. The discussion also touches on failure cases. SFT struggles to match RL's in-distribution performance, possibly because it overfits to reasoning tokens rather than learning general patterns. Meanwhile, RL has its own weakness. It sometimes fails to recover from extreme overfitting caused by too much SFT. In short, RL is great for generalization, but SFT and verification steps play important supporting roles. Thanks for joining us today. Happy learning stretching together.